Section 2.6, Related Rates, Example 1. If air is blown into a spherical soap bubble at the rate of 10 cubic centimeters per second, find the rate of change for the radius when A, r is equal to 1 centimeter, and B, r is equal to 10 centimeters. Alright, so the first thing we need to do is determine what they are asking us to find. Finding the rate of change means that we are looking for a derivative. We are looking for the derivative of the radius with respect to time. So we are trying to find the rate of change of the radius with respect to time. Let's go back and look through the problem again to see what information we were given. It says that the air is being blown into the spherical soap bubble, which means that we have volume changing at a rate. Once again, the word rate means that we have a derivative. So we are given that the rate of change of the volume with respect to time is going to be 10 cubic centimeters per second. Notice that if the air is being blown into the spherical soap bubble, the volume itself is actually increasing. Therefore, the rate of change of the volume should be positive. Now, we were given information about the change in the volume, and we are looking for the change in the radius, which means we need an equation that relates volume and radius together. The volume of a sphere is V equals 4/3 pi r cubed. So we're going to start with that equation and take the derivative of it because we are looking for the derivative rate of change for the radius. So the derivative of V is going to be dV dt equals, on the right-hand side, we're going to use the power rule. Bring the 3 down in front. It will reduce with the denominator of 3, leaving us with a coefficient of 4 pi r squared times dr dt. Remember that when we are taking the derivative with respect to time, we always take the derivative of our variables as a chain rule, a composite function. This equation here relates the change in the volume to the change in the radius. So in the first part, when they tell us that the radius is 1 centimeter, we simply plug the r in, the 1 in for the r, and evaluate. The dV is 10 cubic centimeters per second equals 4 pi, I'm going to put the 1 in place of r, squared dr dt. Now we can divide both sides by the 4 pi, and we end up with our rate of change of the radius with respect to time is going to be 10 divided by 4 pi, which reduces to 5/2 pi centimeters per second. Now, an easy way to remember what the units should be, the differential of the radius is a linear unit, that's centimeters, and the differential of time is a time unit of seconds. So dr dt should be in the same units, centimeters per second. If you wanted to convert this into a decimal, you could also do that. This is going to be approximately 0.7958 centimeters per second. Make sure if you do convert to decimals that you are accurate to 3 places. Now for part B, we're going to go in and look at a different time. We're looking at it at the instant in time when the radius is 10 centimeters. We are still going to use the formula that relates the change in the volume to the change in the radius. The change in the volume is still 10 cubic centimeters per second. And now, instead of the radius being 1, as in part A, I'm going to plug in a radius of 10 and solve from there. Once again, cleaning this up, we have 10 equals 400 pi dr dt, and then divide to get dr dt. So the rate of change of the radius with respect to time will be 10 divided by 400 pi, which will reduce to 1/40 pi. The units, once again, the units for the radius are length, centimeters, and time, seconds. If you would like to convert it to decimals, that's going to be 0.00795 centimeters per second.